We would slowly begin by recapping what we've been discussing on last week. So remember, guys, that we started to discover what do we have in the terms of symmetric key encryption system. So we made the definition. We said that we are looking for some algorithm with the encryption and decryption algorithm denoted by E and D. That the encryption would take a key and a message from a message space and would map that one to an element in a ciphertext space. And then the decryption would do the reverse thing. And so after we have a few descriptions that basically should be the correctness of our algorithm. So for any message and any key that we choose, the encryption and decryption should work. And then we said that encryption is the reverse of the decryption or vice versa. And these two functions are polynomially time computable. So that is very important so that we have a fast algorithm. So once we satisfy all this condition, then we get to the main dish, and that is the security proof. So we have to show under some, difficult or hard problem or hard assumption, or if it is perfectly secure in unconditionally, computational power, we have to prove that this system that we design remains secure. And then we went ahead and defined the different types of symmetric key encryption system. We said that we have so-called stream cipher, and also we have a block cipher. So intuitively they are working the same, but in a stream cipher we are dealing with the messages of a few bits, or maybe sometimes even 1 bit. But in block ciphers we are talking about a block of messages for encryption and decryption. So one of the main difference in the design is that when we are using a stream cipher, we have to use a different key for every piece of message that we encrypt. However, with the definition of and the way that the block ciphers are designed, we can use the same key to encrypt many different blocks of the messages, and we don't have to refresh our key for some good amount of time until we encrypt a lot of messages or plain text. So these are the two differences by the way they function, by the way they work, and by the way that they are designed. I think last week we spent some time here. We defined two use cases for messaging apps and for some file transfer or Netflix-alike streaming website. And we discussed that what is the best choice in every system. So hopefully that would guide you that in future, if you want to use any sort of encryption, you could decide based on the nature of your application. You could decide which of these types would the best suit to your scenario. And then last week we started a very important topic, and unfortunately we couldn't expand more on this. And we landed over here. We said that in order for us to be able to prove that some symmetric key cryptographic algorithm to be perfectly secure, we can follow with this definition. It has to satisfy this condition. So remember, perfectly secure was another definition for unconditional computational power. So no matter how much computational power we give to our adversary, the system would remain secure. So this is the best thing we can achieve. And then the way that it worked was, as we discussed, intuitively we have to satisfy this equation. So what does this equation say? What it says is that if you give the ciphertext to the adversary, and then you hope that the adversary, given the ciphertext C, that it is encryption of some message M, then this ciphertext C, which is extra information, does not provide any useful information for the adversary. So meaning that even though he has spent a lot of computational power, then there's nothing else than just the probability of the message itself that he's gonna learn. And that's why this systems that they satisfy this definition, they will start to call them perfectly secure or unconditionally, secure. So last week we started to discuss a very small example. We said that, let's suppose that our message space is very small. So maybe I have a coin. My coin is not fair. Or maybe there are some questions, and sometimes I say yes or no. The head means yes, tail means no. That's how I respond to these answer to the questions. And what it says, if we want to translate this to the eye of the adversary, is that, well, I use my unfair coin and flip my coin to get, head or tail. And what is this algorithm is saying that at some point we need to provide access to the adversary. So, I draw a sample. Let's say I flip the coin and I get some head or tail. I call it message M. So let message M to be either head or the tail that I just got. And then I use this whatever perfectly secure algorithm it is and encrypt that M and give this ciphertext to the adversary. Now the adversary has this ciphertext of some message that it could be either head or tail. So to the eye of this adversary, then he needs to guess to see, to say whether this ciphertext is the encryption of a head or a tail. But since we are saying that the system is perfectly secure, given the ciphertext C, which is the encryption of a head or a tail, does not help the adversary in any way because, based on the design of the algorithm. So the best guess that the adversary could have is to understand, the distribution of my coin. And he would just stuck to that, okay, if this is the distribution, then no matter what, he better stick to the head because it is 80% chance for the message for the coin to fall on head. And, that would be the highest chance for this adversary to win the game, like this game that we designed. And that would be 80% of the time. But the truth is, he would never be able to, gain any information from the ciphertext that he receives. So how is it so and why is it so? We would get to some examples, you will see, but this is the entire scenario. So if no matter, your adversary is doing ciphertext attack only or, given ciphertext attack, chosen ciphertext attack, chosen plaintext attack, if the ciphertext that you give to the adversary does not provide him any information, so there is no point for the adversary to really interact with the system, right? There is nothing much that he can get from this interaction because the ciphertext doesn't give him any clue. So that's why the adversary would go back and say that, what, I won't gain any information from this encryption itself, but maybe somebody knows publicly the distribution of my coin, and they would just say, let's just stick to the head. So basically encryption, seeing the ciphertexts on the internet wouldn't help. So the adversary would just ignore and just stick to the head. So let's just start to talk about an example, and then I think that would really help us to understand what are we talking about. So maybe make a new page. We are talking about a crypto system to be perfectly secure. So we call it perfect secrecy, right? So a message space M, let's be a bit more generic, is assumed to come from some probability space, is assumed to be probability space. So what does that mean? That means that if we draw different messages from this, message space, which I would start to call them N1, M2, M3, all the way to N different messages that we can have. each message can come with a different probability. So the first one would be P1, and then the second one would be P2, the third one would be P3, and all the way to P of n, where the sum of this Pi is going to be 1, right? So we are these are the distribution where these messages are coming from. We are just trying to be a little bit more generic than, head and tail. So given this information, now we want to see exactly what do we mean by providing the ciphertext. It does not help the adversary. So for that reason, I'm going to introduce you a computation tree. So the computation tree that we would want to use here is we normally start with our message space. Then, we would start to draw different messages. So we would basically land on M1. We can also get to M2. And let's say Mn. So we know that with probability P1, I can get message M1. And, oh no, this is M2. With probability P2, I get to M2. And all of the way to Pn, I can get to, I can get message M. Okay, so this is, planning out all the different messages that somebody can pick from this message space to encrypt. So when you get to message M1, then we assume that we also have n different keys. So by choosing key 1, then we get C1. Let's say if I choose the second key, key 2, then, I can see it. Let me just make it a bit more generalized so we get enough space. So suppose I use key I, then I'm supposed to get CI. And all the way that if I choose key KN, I get CN, right? So let's have a moment here and see what are we talking about. I imagine that, somebody chose message M1 to, from this message space to encrypt. So the message M1 would get, drawn from this message space with probability P1. So suppose we chose this message to encrypt. So, we know that encryption function is a function of message and a key, right? So for encrypting this one message M1, you could basically choose n different keys that we can possibly choose from. So the first one, if you choose key 1, then, encrypt M1 with key 1, then we get C1. If we encrypt M1 with key I, then we get CI. And if we encrypt M1 with KN, supposedly we get CN, and so on and so forth, just because, every key has a different mapping. Remember, we are talking about permutation. So we would have a different mapping for every key. Similarly, this is the situation that we would have for the second message. So we would have, again, if, for example, if I choose K1, maybe I would not call this one C1. Maybe I would just call this one C3 maybe. And then M2, if I choose KJ over here, if my pen doesn't slide, KJ, then I would end up with CJ. And eventually when I choose KN, I would get to C maybe 10, for example. And similarly, we would have the same situation over here. So for the first message, I would have the first key, maybe I get to C9. And then when I chose key KL, I'll get to CL. And then if I choose KN, I'll get to maybe C8. Okay. So this is how the computation tree would look like at the end. So you could see that because of choosing one message and drawing different, trying different keys, this message M1 would get to, map to every different ciphertext that is possible in the space. Because the reason that it will cover the entire cipher space, we said that we have enough keys. We are talking about perfect secrecy, so that we have a enough number of key in our key space. So we would have all possible mappings. So we won't have repetitions over here. And just because of that, some of these C's, even though we don't have repetition over here, but because we are iterating over the same values over the ciphertext, some of these ciphertexts would happen to be equal to each other. That is, Ci is going to be equal to Cj, and that is going to be equal to CL, right? Is this part understandable? I think when we go and give you a message for where we have 1-bit message, then you will see why do we mean by having these values. It has to be equal in all of these cases. So since, again, that we would have the repetition of the CI for every possible message, what does that mean? That means that when you see the CI, because I have different choices of keys to make. So seeing the CI, it is possible that if I choose KI, it is the encryption of message 1. If I use key J, it is possible that is the encryption of M2. And if I choose key KL, it is going to be the encryption of message N, right? So given this piece of information, well, we know that any message can get encrypted to this ciphertext, particular ciphertext, and that is happened by the key that we chose, right? That provide the mapping. So now, if we look at the formula, probability of M to be this particular M and C to be this ciphertext is equal to probability of message to be just the message itself. That we chose this message M. So looking into this again, what does this formula says is that, we know that if somebody give us CI, well, we know that any particular message from this message space by choosing different keys can happen to have the ciphertext CI, this specific ciphertext. So giving the adversary this piece of information ciphertext doesn't really help, right? The best shot or the best thing that the adversary would have is that he better stick to the message that has a higher probability to happen, right? For example, if in this space, message 2 has the highest probability among all other messages, then, the adversary better to stick to the message M2. And since that, this is the encryption of message M2, because given this ciphertext, again, it didn't provide any additional information to the adversary. The adversary already knew that, okay, this ciphertext could be encryption of every possible message. So what message is highly likely to be this message M, the encryption of message M to be this C? Well, he would look at the distribution of the messages and he would say that, I think, it would make sense that I stick to the message that has the highest probability, because then that message would be chosen with the higher probability to get encrypted, and it is highly likely that I could win the game and provide the correct guess. How do we compute that correct guess? Very soon we will get to it. But what I want you guys to see is that what we are seeing over here is that we have message space. We are mapping the elements from message space into the cipher space using a key, right? K. And this key is just doing the mapping for us. So if you don't know this key, we really don't know what element is mapping to what other element. So if the adversary really wants to win the game, he is better to also have another strategy to win, and he understands that what keys are chosen with the higher probability. Then, if that is the case, and he knows that some keys are being chosen with a higher probability than the other keys, then he can start to do some computation on the side and says that, well, I know that, for example, key J can happen more likely. So then, that would affect this computation. So knowing this probability distribution and probability of the key, then he can say that, okay, I can use my computational power to come up with a better guess. But we always say that, when you want to do encryption or decryption, we say that we choose a key randomly, right? So the distribution of this key is normally unknown and also uniform. The best thing to achieve is to have the key to be uniform. That is, every key can be selected by the user with the equal likelihood, with the equal probability. So, and if that happens, then, again, the computational power that the adversary would have doesn't really help, because every key has equal likelihood to happen. So basically, all the adversary will learn, again, goes back to the distribution of the message space itself. So it wouldn't really help. Let's go through a smaller example. So now that we have understood in a big picture, so I really want you guys to see this example. I think this would really help you to understand the things even better. So let me take a new page. Okay, so now we are talking about an example. Suppose that our message space is just, one bit. So the message is, remember, it was a head or tail, right? And that's it. It's a 0 or 1. So, depending on what is happening, we want to choose, let's say we are just encrypting 1 bit, and the ciphertext could be 0 or 1. And now we are defining that the probability of the message space M is actually just P and P minus 1. What does that mean? Is that somebody would draw a message M0 with probability P, and somebody would draw a message M1 from this message space with probability 1 minus P. So we just define P and 1 minus P. You can define P and do the exact computation, but we just try to stick to a generic way, and we would be able to solve it for any P. So now we want to ask ourselves this question. So given a ciphertext C, to the adversary, we know that it shouldn't provide any information to the adversary, but suppose we don't accept that formula. So, let's pretend to be the attacker now, and let's find out what is the best strategy to predict the plaintext given the ciphertext. So there are 2 ways to do it. The first one, we are going to, use the easy way and just say random guess. What if I just don't care about computation? I just randomly guess every ciphertext that I see. It is, it is a encryption of M0 or M1. And then I want to compute how much is my winning probability, okay? And then the second one is that we are going to really follow up with this formula and see, by using this formula and the computational tree and the fact that we have unconditional computational power, what would be my best strategy to win the game. So for that reason, let's begin to see this new example. So we start with a random guessing. So we said that the message space is, we have 0 and 1, right? And then the ciphertext space is going to also be 0 and 1. And the key space in this example is also 0 and 1, right? So we are checking the bits from 0 and 1. So we say that we want to do random guessing. So probability, the adversary A, by given the ciphertext, this is the way that the algorithm works. The adversary's algorithm. He would output 0, and with probability a half, and also he would output 1 with probability of half again, right? He said that he would just do a random guess. And we want to really do a computation and find out what is his winning probability. So in order to do that computation, so we start with our message space. So we said that we can either choose M0, and then we can either choose M1, right? We choose M0 with probability P, and then we choose M1 with probability 1 minus P. And then once we get to here, we have these choices. So we would be able to encrypt the message M1 using key K0, or depending if the key is 1, then if the key is 0 and the message is 0, maybe we get to C0, and then otherwise we get to C1. So let's be generic and let's say with probability Q we get K0, we choose K0, we don't get it uniformly random. And with probability 1 minus Q we select key 1. So this is what we get. And over here, if I choose K0 with probability, of course, Q, and I can choose K1 with probability 1 minus Q. And then if our message is 1 and I choose the key 0, and let's say I get C1, and over here I get C0, right? All right. So now these are the all possible way that we would, or encryption would happen. So the computation tree is actually drawing every possible message. For every possible message, we draw every possible key, and then we try to use that algorithm to do the encryption, right? So if you have this whole computational tree, which sometimes if your message is long, this would take a very long time to come up with this computational tree. But you know what? Right now we say that we have a perfect secrecy. So no matter how long and how long the message space and the key space are, the adversary has no problem to plot this entire computational tree. So that's why we are saying that our adversary now has unlimited computational power. So now let me draw a line over here so that we would start to discuss our adversary right over here. So this is the computational tree that adversary has computed in advance, let's say, and then when he was offline, now he has this computational tree and he entered the game. And we want to see how much his winning probability is. So we said that every time that he sees a ciphertext, this is our algorithm, adversary algorithm A. Every time that he sees a ciphertext, with the probability he outputs the message, the message correspond to the ciphertext is 0 with probability half, and then he would output 1 again with probability half. So when we are here, we give the C0 to the adversary with probability 1 or a half. He would say this is M0. Again with probability half, he says this is M1, right? Again, for this case, with probability half, he says this is M0. And then again, with probability of half, he says it is M1. Again, so, this is a strategy. So we don't judge the adversary. We just try to, come up with all possible answers that he would give, because he has unconditional computational power. So no matter how large this table is, he can do the computation offline and carry out this entire computation. Okay. So now that we have done this computation, so the only thing that we want to see is the probability that this adversary is actually correct and he output a good answer, right? So to answer that question, we need to compute the probability that A is correct. How do we compute that A is correct? Let's see in what branches on this computational tree this adversary happened to be correct. So the message was M0, and then the ciphertext is C0, and then the adversary here says that the message corresponding to the ciphertext C0 is M0 or M1. So we know that the message was M0. So let's just draw a triangle over here indicating that adversary was correct in this branch. And similarly over here, so this one is correct, right? So over here, you see that we have, so we have M1, and over here he says M1. And again, over here, we have M1, and here he says that it is M1. So, I'm sorry, over here it is this one. Message is M0. So let's now see how much is his winning, in how many times, what is the probability that A is correct. So in order to do so, we need to compute the probability of this branch in entire. So probability P, the message M0 is chosen, with probability Q, K0 is chosen, and the probability of half, the adversary would say that this is M0, right? So if we do this, we're going to have P times Q, this P, because we get to this branch, and then we have M0, so we choose K0, Q, and then with the probability of half, that is going to be correct. So again, probability of half plus. What is the probability on this branch, right? So we have again P times 1 minus Q times a half, right? And then we follow with the other branches. So over here, this branch happened to be the correct answer. So we have 1 minus P, and then we have Q, and then we have a half plus. What is the probability that this branch is, the last branch is correct? So with probability 1 minus P, message M1 was chosen. Then with probability of 1 minus Q, the key was chosen. And then the probability of half, the adversary correctly guessed that the message is M1, right? So if we just rearrange this formula over here, so how can we rearrange this one? So I can see that this one has Q and this one has Q. So what I can do is that I get this P over 2 factor, and then I would have Q from here plus 1 minus Q from here, right? So let's review. So I try to get these two together. So I have P half in common. So then I would have Q from here and 1 minus Q from here. Plus, from the other side, I have 1 minus P over 2 is common. So 1 minus P divided by 2. So again, I end up by Q from here plus here I end up with 1 minus Q, right? So as you could see, Q plus 1 minus Q would just become 1. So it just gets canceled. This is 1. So what I end up with is basically P plus 1 minus P over 2, which is just a half, right? So we have correctly computed with what probability, supposing these are the distribution of the message and the key, then if A happened to guess like randomly, just randomly saying a half, or with the 50% probability, he says every time that he sees a ciphertext, he says that the ciphertext is M0 or M1, then after we did the entire computational tree and we try to win the game with this strategy of the attacker, we have found that the probability that the adversary is correct is only 50% of the time. So this didn't really surprise us. And keep in mind that when we carry out this computation, you can see that we are trying to be generic. So no matter what actual value you assign to this P or what actual values you assign to this Q, An attacker that would randomly guess, he would not win with his, probability that this attacker is correct would not change, no matter what really values you would assign over here. So I think this didn't really surprise us. We knew that if somebody just guessed randomly, he shouldn't win with, higher chance. But I think it was a very good practice for you guys to see how we use the computational tree. So the game over here, one more time, I want to explain is that since we said that the adversary has unlimited amount of power, he can go, and plot this, draw this computational power. Imagine M is a bit larger and the key is larger. This computational tree would become very big, right? So imagine, for example, for these days, I ask you for AES, go and plot, the computational power. So you have 2 to the n, 2 to the 128 different messages. And for every message, you have, let's say you choose the key to be 128-bit again. So you have 2 to the 128 different computation. So that would be already a lot challenging to store such a table. And even though you have that table, it would really take a long time for you to go through every branch and do that search. That is the reason that we said that I assume this adversary to be unconditionally, we have unconditional power. And plotting this computational tree is a piece of cake for the adversary. And also he has his own way to, go through this different branches and do different computation. And those wouldn't take any much time. So even though he can do that, you will see that at the end, his probability that he would be correct is just like 50%. That did not change anything of how we chose the key, how we chose the message, and so on and so forth. Is this the best way to win this game? Obviously not. So the question, let me see if we have any questions first. Supposing that we are using, perfectly secure encryption system, this is the story. So for now, we are assuming that this system is perfectly secure, and that's why we allow, the adversary to do this computation. Not allow, we assume that he can do this computation. Let's go and answer. So we said that the probability that he would win with a random guess is just like by half, right? So is there any other strategy? So let's go and play with the second one. So in the second one, we said that consider the computation, the conditional probability. And given that computational tree, now we are going to have a much better guess and see where we would end up with. So I'm going to call this attack to be a good guess. If the previous one was a random guess, I'm going to call this one to be a good guess. That is, given C, let's say 0, then we're going to do this one. We would want to use the computational power to see if we can actually do anything. So we're going to compute probability of M to be M0, given that C is C0, and we're going to call this one to be alpha. And at the same time, we are going to compute probability of M to be M1, given that C equals to C0, and we're going to assume that this is going to be beta, right? And then we're going to say that 2, this is the algorithm A. If alpha is greater than beta, then guess M0, right? And else guess M1, right? I'm sorry, it should be a small one. So very interesting, right? Now that we have the computational tree, we're gonna, get advantage of that computational tree that the adversary has computed, in offline. now that he's playing the game. So we want to use this probability to see if he can win this game with a higher probability. So before I go through the computation for this probability, I want to remind you of some probability theorem called Bayes theorem. So I hope that you guys remember this probability theorem. So we have Bayes theorem that says that this is the theorem. It says that probabilities of some even A given even B is equal to the intersection, probability of intersection of those sets or events over the probability of B, right? I think you guys remember this one. And again, using the very same formula over here, I can rearrange this one, saying that this is probability of B, and the top, I can rearrange it to be probability of B given A times probability of A, right? Again, using Bayes theorem. So this is the Bayes theorem, and we accept this, that is true. And if somebody forgot the Bayes theorem, I invite you to go back to the probability material and check this out. So now that we have this this theorem, now it would help us to actually solve this probability distribution. So that means that I have two choices. I know that alpha equals to, we define it to be probability of M equal to M0, given that C equal to C0 is equal to, based on this Bayes theorem, you see that probability of even A given B, I can rewrite it in this form. So this is just like, imagine is A, and this part is imagine you B. So this is A, and this is B. So I can rewrite it, and I can tell that this is going to be probability of C to be C0, given that M equals to M0, multiplied to probability of M to be M0, and this is divided by probability of C equals to C0, right? So I didn't do much. I just, applied the Bayes theorem, and I could convert this probability. I can rewrite it in a different format. And I can do the same thing with beta. So I'm going to define beta to be, we said that it is probability of M to be M1, given that C equals to C0 is going to be equal to probability of C to be C0, given that M is M1, and time the probability of M equals to M1 over probability of C to become C0, right? So this is the computation that I have carried out so far. And let's see if I look at the computational tree, if that can actually help me to do this computation. So it says that given that M is M0, what is the probability of P to be C0? So let me go back to my computational tree. It says that given that M is M0, okay, we know that M is to be M0, and now the C is actually C0. With what probability from M0 we get to C0? The only way is that the key is actually equal to to K0, right? So the only way that this line can happen is when key is selected to be K0. So it is depending on when P of probability of key to be chosen to be K0, right? And we know this one is actually Q. And then the second one, it says that given that the message is M1, so the adversary can, go back and he has this computational tree. He says that we know that the message is M1. So, okay, so this is done. What is the probability of this ciphertext to be C0? He look at this one, it says that, okay, the only probability that this message M1 can get encrypted to C0 is actually when the key is chosen to be K1. And that is probability is 1 minus Q. So the only time that this even occurs is when the key is chosen to be K1. If my pen doesn't slide sometimes, K1. And we know this one is 1 minus Q. That is the probability. Okay. And the rest of them, we don't really need to know their probability. So given this, I can tell that, okay, so I know that the first piece over here, it happened with probability of Q multiplied to probability of M to be M0. So I go back to the computational tree. The probability that I get M0 is just P. So I would just replace it with P. And then probability of C equals to C0, I just treat this one as a constant. So I just don't really have to do this computation. So probability of C equals to C0. I just let it be. And for the second one, I can do the same computation. And I get the first one is 1 minus Q. And then the probability of M to be 1 based on the computational tree is 1 minus P. And P probability of C equals to C0, right? So remember that these two pieces of denominators, they are equal. So I don't really have to spend time to do this computation. I can just treat them as a constant. Right? So now I assume, we just want to somehow simplify these equations to see if we can, understand them better. So I can assume that the key is chosen uniformly random. So I can say that when Q is 1/2, which means that key is chosen randomly. So without knowing the Q, I can, every time I do this computation, and based upon the answer for this computation, I say, it is better the encryption of M0 or M1. But just to make this computation a little bit more, make it a bit more tangible, I would say that I assume that I choose my keys uniformly random. And if that is the case, then these formulas would get simplified to alpha equals to P over 2 times probability of C equals to C0, and beta equals to probability of 1 minus P over 2 times the probability of C equals to C0, right? And basically, since these denominators are correct, the only way that the best way for the adversary to answer is what? He better answer if P is greater than 1 minus P, then he better always alpha would become greater, and then therefore the best strategy for the attacker is to just say that the encryption was for the message M0. Otherwise, if this one is greater, which means that P is less than 1/2, then it means that the adversary is better to answer beta. The beta becomes larger. So based on this strategy of the attacker would say M0. So altogether, the probability of A is correct. We can compute it to be maximum of P and 1 minus P, right? So the best strategy for the attacker to answer is basically, after doing all this computation, assuming for easier computation where key is uniformly random. So the best strategy for the attacker to win this game is, again, going back to the distribution of the message space, remember? So if the M0 is, the P is larger than 1/2, it means that M0 is chosen more often than M1. So the adversary would just always answer M0. Otherwise, the adversary would answer M1. So you see that what this means is that this is equal to probability of message space, right? Because if the adversary knows that the distribution of the message m in the first place, p and 1 minus p, if he knows p is, for example, 2/3, then what we have shown is that accessing to this computational tree didn't really help the adversary. Even though he used the computational tree to do all this computation, he ended up with the distribution of the message itself. So therefore, all this computation power that the attacker put in place did not help him at all. And therefore, our system is perfectly secure. Okay. So I can see that it's a little bit after your break time.